Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay. Good afternoon, everyone. About more than a week ago, we heard Professor Lovas gave a survey talk on optimization on huge graphs, and I thought, well, everyone who missed it should hear that talk, but didn't want him to ask him to give the same talk again. So there was an aspect there which I thought was really remarkable, and I thought it would be great for more people to hear about. So I'm delighted to have Laszlo Lovas tell us about the similarity distance on graphs and graphons.
Thank you. Let me start with just with the problem. So imagine a very huge graph, and suppose you want to, and this should be a dense graph. So we suppose it has order of n squared edges, and we would like to somehow define when two of its nodes are similar. The goal of this would be that if you want to do an algorithm on this graph, then it would be helpful to be able to pick a small subset of the nodes so that they sort of represent every other node in some similarity sense. So when should we call two nodes similar? Well, one first idea is that maybe if they are close in the graph. But remember, this is a dense graph, and so most nodes will be close to each other. And on the other hand, two adjacent nodes may look very different. They may have very different degrees or something like that. So a next idea is that maybe you should look at the neighborhoods and say that two nodes are close if their neighborhoods overlap a lot. That's a better notion, but it's still not quite good because typically the neighborhoods will not overlap a lot. For example, if you take a random graph, then all its nodes are similar. Nevertheless, their neighborhoods don't overlap. So not giving up, let's look at the second neighborhoods. And it turns out that this is a good notion. So I defined the similarity distance of two nodes u and v in this graph as follows. So here are the nodes u and v. I pick randomly a w, and I count how many paths of length 2 are there to u, and how many paths of length 2 are there from w to v. And then I take the difference, and I would like this difference to be small for most w's. So in other words, two nodes will be similar if the number of pathways to get in 2 steps to a node w will be about the same for every, or on the average for every w. So to be exact, I define that this is the expectation of w, and then here I have to take the expectation. I mean, I would like to write it as an expectation, so let's pick here a random node x, and then the expectation of in x, it should be a probability here. So you can take the probability in x that x is connected to u and x is connected to w minus the probability in call it other random point y, that y is connected to v and y is connected to w, and I take the absolute value like this. It's a little tricky to work with, but it turns out to be good, as we'll see. So one of the first things to notice is that this indeed defines a distance, so it's a metric. So and it's easy to verify that it's a metric. So you could also introduce a similar distance by saying that you start from u and do 2 random steps, start from v and do 2 random steps, and then you look sort of the variational distance of the distributions you get. That's not exactly the same because that will depend on the average degree of what you reach, but we are in a dense graph, so the average degree is like a constant, so that wouldn't be very different. And maybe for it suggests that is how to generalize this for sparser graphs where you have to take more steps because otherwise you don't overlap. But for that, let me stick with this definition and for dense graphs. So to formulate the main property of this that I need a few definitions. It's not the simplest way to get there, but if you have 2 graphs, but I will need it later too, on the same set of nodes, then we want to define, it's another distance, but that's now between graphs and not between points of a graph. And it's called the cut distance of the graphs. And what I do is I count the number of edges in G between some 2 sets S and T, and I'll count the number of edges in G prime between the same 2 sets. And I take this difference, and I need here more space, so I need to take the maximum of this over all sets S and T, and I have to normalize this, and I normalize by the square of this common underlying set size. That's called the cut distance. So it is the 2 common underlying set, and you take 2 sets S and T. And so this distance is small if between any 2 sets S and T, the 2 graphs have about the same number of edges. Now it was introduced by Fries and Cannon, and the main point, their main point was that they could express a version of the regularity lemma. So now I come to the regularity lemma. Now, luckily, this is a weaker but easier version, so I won't state the regularity lemma in its stronger versions, which are a little bit difficult or just lengthy to state, not terribly difficult. But for this version of the regularity lemma, I will need the following. This will be this distance. Another thing is that suppose that P is a partition of the node set of a graph. And then I would like to define another graph, G sub P, on the same node set, but now this is a complete graph with edge weights. And if I take 2 nodes, then the edge weight would be the density between their classes. So if X is a node in class Vi and Y is a node in class Vj, then the weight of the edge xy in this modified graph GP is, I count the number of edges, now there's only one graph in G, between Vi and Vj, and I normalize by the total number of pairs between them. And that's the density between Vi and Vj. And for whatever x and y, I always put this weight on it. So if you want the total weight between Vi and Vj will be equal to the total weight in the original graph, but it's now sort of averaged out. And so the Fries-Cannon regularity lemma says that, well, let me formulate it like this. For every k, there exists a k partition for every graph. For every graph and for every k, there exists a k partition P such that the cut distance between G and this GP is bounded by, I think it's 2 over square root of log k. The point is that, and I haven't really defined this, but it's pretty clear. So if G prime is a weighted graph, then instead of counting the edges, I add up the weights between the two subsets. So there is such a partition so that if I take any two sets, then the number of edges between them in the original graph is about the same as the as in this averaged out graph. So in other words, it's about what you expect on the average. So this is the regularity lemma. Yeah, you can do it the other way. With epsilon, so you can call this epsilon, and then the number of parts will be 2 to the 1 over epsilon squared, or 2 to the 2 over epsilon squared. You can put extra conditions like you can require that the partition classes are about the same and so on, but I don't want to spend too much time on this. So this is the regularity lemma, and I will need one more notation, and that's the following. So let now f and g be two graphs, and I'll think of f as small, of some fixed size, and g very large. And I denote by TFG is, one way to define it is the probability that a random map from VF to VG preserves edges. In other words, I count the edge-preserving maps, homomorphisms, and divide by the total number of maps, and that's this TFG. So it's a number between 0 and 1. It's the density of F in G. So if F is a single edge, this is just the edge density of G. And again, G is very large, so I don't have to worry about whether this is a one-to-one map or not one-to-one map. By definition, it doesn't have to be a one-to-one map, but if you think about it like that, it doesn't make much difference. And so let me, and there is what is called a counting lemma. Which is comes from the theory of regularity partitions, but it's actually independent of regularity partitions. It just says that that for every f, g, and g prime, the density of f in g minus the density of f in g prime is bounded by the number of edges of f. And remember, I think of this as small times the, I assume that g, they are on the same, g and g prime on the same set. Then it's the number of edges of f times the cut distance of g and g prime. So you see, the point here is that if you have a good approximation of G by this kind of averaged out graph, it's very easy to compute, or fairly easy to compute, the density of F in this, because there are only a small number of ways you can try to place F, and then so say you want to know the density of triangles. I mean, you pick 3 points, but it doesn't matter which 3 points you take, as long as you pick them from the same classes. And for each class, it's easy to, it's just the product of these densities. So once you have this approximating graph, G sub p, you can actually compute the density of triangles in here, and by the counting lemma, it's approximately the same as the density of triangles in the big graph. So that's a typical way to apply this lemma. Okay, so now let me come back to this similarity distance. In my talk, on Saturday, 10 or 11 days ago, I mentioned a result which basically says that kind of epsilon-net relative to the similarity distance defines a regularity partition by Voronoi diagrams. So let me state this exactly. So, am I here? So here is the theorem that connects those. I have to go both ways. So first, suppose that P is a partition, which is a weak regularity partition, so that the distance of G and GP, let's call this epsilon. So it doesn't matter at this point whether epsilon is this or maybe it's could be better, could be worse. So whatever is the epsilon, then I can select representatives from these partition classes such that I look at the distance, not any distance, the similarity distance of a node X from this representative set, and I take the expectation of this for a random point, and then this will be bounded by 4 epsilon. And second, if I take any set Vg such that the same thing, the same thing holds less than or equal to epsilon or equal to epsilon. So now we go the other way. So suppose this same expectation is epsilon, then it means that the Voronoi cells of S are they form a partition. So give a partition P such that the cut distance between G and GP is bounded by 8 times square root of epsilon. So, remark. So what are the Voronoi cells? I mean, they come from geometry, but you can define them when you have a matrix. So you have a subset of the points, and then you find a partition. You put each point. So each of these will be the center of a class, and you put each point into the class to which it's closest. And so this is the about Voronoi cells, and you see this set S has the property that most points, or on the average points, are close to it. That's how the nicest correspondence goes. But of course, this means that ignoring some maybe square root of epsilon fraction of the points, the rest will be closer than square root of epsilon. So you get also that most points will actually be close to this set. So
so the set is the minimum
is the minimum of the distances. Yes. So this is the theorem which connects these two things. And let me give you, I won't give you the proof. It's a fair amount of computation somehow with Cauchy-Schwarz inequalities and the like. Let me just try to give you the heuristic for the first implication. So suppose here you have this weak regularity partition. Now, what it means is that the graphs between any two class and perhaps even within the classes are random-like to some degree. Now, so all the stronger versions depend, I mean, really you get the stronger versions by getting stronger notions of what it means that it's random-like. So this is a very weak notion of random-like, what we formulate with these two sets S and T. But let's think of it as random. They have, of course, different densities. So these are random with different densities. Now, let's pick a, say, typical point in each of these and call them, this is the center. Now, if you pick any other point in the same class, what I claim that it is close to this center. Why should it be close to this center? Because to every, so this is U and V, and if you look at the definition, I have to pick a third point W, it's in some class, and then I have to compute the number of paths of length 2. So this is W, and I have to compute the number of paths of length 2 to W. But, well, say they go through this third class. I have to separately count paths in different classes. If it goes through this third class, then because this is random-like, there will be sort of this will be connected in this class with some subset, which depends on the density between here. And this point will be connected to another subset, which depends on the density between here. And you can argue that if you choose W randomly, then this is also random enough so that the intersection is predictable. And that's what really means that the 2 points are close. So this is just the heuristic of the proof. Now there is, okay, now I have, so one thing, so let's say that, that the set P is a good representative set, epsilon representative set, if this condition holds. So if the average distance from it is less than epsilon. Now what, using the regularity lemma, you see that there will be, I mean, if this is epsilon, really maybe I should have told here the more traditional thing. So if this is epsilon, then this k is something like 2 to the 2 over epsilon squared. And so it means that for every epsilon, you have a representative set of size about 2 to the 2 over epsilon squared. So we did get something here, because what it says is that no matter how large the graph is, you can pick a bounded number of points, bounded in terms of the error bound, so that every point is similar to, or almost every point, so most points are similar to this subset, to at least one of these points, at least on the average. Now, there are two questions here. So what is such a representative set good for? And second is, I mean, this is still a fairly big bound. Can you say something better? So let me first try to say a few words about what is this good for. And that I described this algorithm at UW. So for example, suppose you want to compute a maximum cut in a graph G. And again, G is a huge graph. And suppose that the access to G, your access to G is that you can sample from G. You can pick randomly maybe 100 nodes of G, and then you look at those 100 nodes, and you want to get some idea about maximum cut in the big graph. Now, this is a classical problem in the theory of property testing, and it's non-trivial to prove, but it's not. It has been known since I think late 80s or early 90s that you can, if you pick a sufficiently large sample and compute the maximum cut in that sample, then the density of that maximum cut will be close to the density of the maximum cut in G. And in fact, the bounds are quite decent. So it's polynomial in epsilon. 1 over epsilon to the 4th maybe is the necessary size of the sample. But now suppose that we need a little bit more. I mean, we want actually to see the maximum cut in the graph G. Now, the question is, what does it mean we want a maximum cut in the graph G? Because a graph, we assume, is so huge, we only have access to it, sort of random access to it. So what a small number of points. So how do we return the answer? Well, how do we specify the maximum cut? And one model is that you can, what you can do is that I offer a service to you. So you give me a large graph. I do some computation on it for a finite time, and then you can come and ask me, is this node on the left-hand side or the right-hand side of the cut? And I answer right-hand side or left-hand side. And you can repeat this any number of times. And this should be, whatever answers I give you, it should be consistent with some choice of an almost maximum cut. Well, I mean, I may err because everything is randomized, so there is some probability that 1 or 2 points will be misplaced. But for most of the points, I mean, there should be a cut for which most of the time the answer is correct. And so how to do this? Well, the idea is to select a representative set. Now, how do we select a representative set? Well, there are algorithms known to compute the regularity partition, and then maybe one could use some constructive version of this theorem. But those algorithms, like they work in another model where you actually know the whole graph. But in the sampling model, but it's actually very easy. So first remark is that if you have a set where the distance of any 2 points is, well, let's say it's greater than epsilon, but for every outside point, the distance to the set is less than or equal to epsilon. No, well, that's what no. You take a maximal such set. So take a maximal set in which any 2 points are at the distance greater than epsilon, or at least epsilon. Then clearly every other point is closer than epsilon. So it's such a set, in fact, not only on the average, but for every point. Now, this would be too much to hope for, to be able to pick such a set which is truly maximal, because there could be some remote corner of the graph which you will never be able to reach by sampling. But nevertheless, what you can do is you can start picking these points. And you can pick them at random. And if you have picked a certain number of points at random, then if you pick a new point and it's farther than epsilon from all previous points, then you keep it. Otherwise, you discard it and you pick another one. And if you are unsuccessful for maybe 1 over epsilon squared steps, then you stop. There will be only a small fraction, maybe still a small fraction of points which are far, but it will be very small, and so it doesn't influence the average distance. So this way you can get a representative set, and with a little analysis you see that this is oh, by the way, I mean, I am saying conditioning, I mean putting condition on the distances, but the way I wrote it here, you see that the distances can be computed by sampling. So in our sampling model, somebody comes with 2 points, we can answer what the distance is, and so we get this this representative set. Now, for these representative sets, we have the Voronoi cells, which are, of course, we don't compute the Voronoi cells, but we can compute the densities between the Voronoi cells, because we just sample enough points, and there will be lots of points sampled from here, lots of points sampled from here, and then we see how often we get an edge between them. So we can compute these densities. I mean, this is not very efficient here, but I only care about finite computation at the moment as a function of epsilon. So you can compute these densities, which means that basically you will know this graph G sub p, and then in G sub p it's easy to compute a maximum cut. And the cut distance, actually the name comes from this, because obviously the maximum cut in this G sub p in this graph is the same as the maximum, or I mean up to the little error. It's very close to the maximum cut in the big graph. So we have this maximum cut, which means that these representatives are now two-colored. And now the point is that you just say that everybody is on the same side as his boss, period. So if you come to me with a point, I compute the distances, and whoever is, if the red point is closest, I call it a red point. And this gives an almost maximum cut. And this is the way to use this. Another remark is that from the fact that this theorem sort of goes back and forth, it's not hard to prove that this algorithm, I mean, with a little care, will actually not only give you a representative set, but it will give you a representative set which is not larger than any other representative set for a little smaller epsilon. So if you are willing to sacrifice a factor of 2 in the epsilon, then you actually get the best possible representative set, or approximately in the smaller. So if the representative sets, for example, if you are lucky and your graph is better and the representative sets depend only polynomially on epsilon, which could happen, I will come back to this in a minute. If they only depend polynomial on epsilon, then you only do polynomial time in epsilon computation here. So this is a consequence of this, that the theorem goes back and forth. Okay, so the question whether you really need here for some graph, you really need here 2 to the 2 over epsilon squared, or maybe some polynomial in epsilon, it's some kind of dimensionality, because if you think about it, this is a metric space. Now, if the metric space is one-dimensional, then you only need 1 over epsilon points, or in other words, you can pack at most 1 over epsilon points so that the distance of any 2 is at least epsilon. If it's two-dimensional like the sphere, then you get 1 over epsilon squared. So this is a notion of a dimension, which is actually called the packing dimension. Can be defined for every metric space. And the packing dimension is defined as follows. So first we define a function n of epsilon is the maximum number of points, at least epsilon apart. Assume it's a finite number, so it's say a compact metric space, finite. And then we take this log of an epsilon and normalize by the log of 1 over epsilon. That really means that we are looking at the exponent, how fast this grows as a function of 1 over epsilon. And then take the lim sup of this as epsilon goes to 0. Of course, if it's finite, then for small epsilon you don't get anything. But I will go in a minute. I still have a little time. I will talk a little bit about how to get a true definition of dimensionality out of this. So it's a useful definition. Now for this, I have to spend 5 minutes, but not more, introducing some strange guys called Graphons. So a graphon is actually a function w defined on the unit square with values in 0, 1, such that, well, it's symmetric and measurable. And these were introduced here in this group, so but I will. So okay, so these are generalizations of graphs in some sense, and they serve as limits of graph sequences, all of which I don't want to talk really about. But I do need to introduce these graphons in order to. So you should think this as some kind of adjacency matrix of a graph. So it's like here is the unit square. But the graph is now defined on the continuum. And it seems that it's a weighted graph because W can be anywhere between 0 and 1. But actually, perhaps a better way of thinking about it is that there is an infinitesimally small neighborhood of x, the infinitesimally small neighborhood of y, and between them the density is wxy. So this is a graphon, and you can generalize all these things to graphons, which is fairly straightforward. So for example, this is one thing I will need. The density of f in a graphon, so the large graph will eventually become this graphon, can be defined as an integral, well, over 0, 1 to the vf. So there will be a variable assigned to every node of v. And then you take the product of w, xi, xj over all edges of f, and you integrate this out. So in other words, you choose in all possible ways endpoints, and then this is, I mean, if you think about it as the adjacency matrix, then this is 1 or 0. So this is 0 if they are not adjacent. So this is non-zero only if they are, for every edge is mapped onto an edge. And so that's exactly that probability. And okay. And you can appropriately define W sub p for a partition p. Well, you take the partition, and then you average out the function on each of these rectangles, and that gives you W sub p. And now here is, and unfortunately I raised it, but exactly the same formula also defines you a similarity distance between 2 points of a W. So you pick, well, it's you pick a third point W. So this is going to be the similarity distance between points where it U and V. These are now points of the 0, 1 interval. You pick randomly a third one, and then you take, actually in this case you have to take expectation in X of W U X times W X W. So this is sort of counts path of length 2 from U to W. And minus you take the expectation, maybe another variable y, of W U Y times W Y, absolute value, another. So, so it's exactly the same thing. You can express it in terms of W. That gives you a similarity distance. between 2 points. And now here comes some nice facts. If you take, well, I will write the 0, 1 interval, but now it's not with the usual metric, but with this similarity metric. Then it's a compact space. That's more or less true. You have to change W on a 0 set and so on. So you have to do some cleanup. But you do get a compact space here with respect to this distance. And the dimension of this space is what, and now for this space, this definition makes sense because it's now an infinite space, infinite compact space. So you can look at its dimension in this sense. So let's call this space J. And so you can look at the dimension of J. And you can ask whether it's finite or infinite. Now, the regularity lemma is true for W's. So you can replace this G, simply put here a W, and everything stays like that. And it's true that if the dimension of W is finite, then say D. So if the dimension of W is D, then actually you get K to be 1 over epsilon to the D. Well, big O. So in other words, here now you have an exact notion of dimension, and this exact notion of dimension corresponds very nicely to the regularity lemma. Okay, and now the question is, what can we say about which W's are finite dimensional? Now, why do we care about W's? Here I will only describe the idea that the fact that if you have a sequence of graphs where the number of nodes tends to infinity, then you can look at a fixed f and take its density in Gn. And now suppose that this tends to some limit for every f. Then we say that this sequence Gn is convergent. And the theorem is that this can always, the limit can always be represented by a W. So there's always a W to which it tends. So Gn, in this sense, tends to some limit W. And moreover, it's not only that these densities tend to the W, but max cuts and all sorts of things. So the Gn, it's a very large graph, can be very well approximated by this W, I mean, for a convergent sequence. And therefore, if we know that the limit has finite dimension, then we also know that not only the limit has polynomial size regularity partitions, but all these graphs have, of course, for a fixed epsilon, a finite graph, I mean, has to be large enough in order to have any meaningful regularity partition. But as n tends to infinity, for every epsilon, eventually the Gn's behave like that. So the question is which W's have finite dimension. And of course, it's easy to construct such functions W. I mean, if you sort of try to give this W by some formula, almost surely it will be one-dimensional or something. So in order to construct an infinite dimensional W, you have to do some kind of fractal-like thing here. So, but there are a couple of results that actually, well, I will tell one result and one conjecture about this. So first, the result. So suppose that F is a bipartite graph with bipartition V1 union V2. Now, we can say that we can sort of define some sort of induced density of F in W. Which means that, okay, let me write up the formula. It's an integral product of W xi yj over ij an edge. So in this case, I will have 0, 1 to the V1 cross 0, 1 to the V2. So I will have a variable still for every point, but I just denote them differently in the x's and y's. But I also put here a product over the non-edges, W of, 1 minus W. Yj, and then I integrate with respect to all variables. So, and I forgot here. So what does it mean? It means that think of W as a finite graph. So what should it mean? It should mean that the edges in this bipartite graph should go onto edges because these have to be non-zero. But those pairs across V1 and V2 which are not adjacent, they should go on to non-edges. And the condition doesn't say anything about what should happen to pairs which are within the same class. So this is some kind of induced subgraph in a bipartite sense. And so one theorem says that if T induced F W is 0 for some bipartite graph, so if there exists an F, bipartite F such that, then it follows that this W has the dimension of, I called it dimension of W, which is the dimension of this space, is finite. More follows. It also follows that W is 0, 1 valued. Which is another useful property to have. But so what it means is that you make, so if you, combining with the graph limit way of looking at it, it says that if there is a sequence of graphs which do not contain this F as an induced subgraph in this bipartite sense, then the limit has finite dimension, but at least it means that they have polynomial-size regularity partitions. So that's a sufficient condition for that. The proof of this theorem is actually not hard. It uses some Vapnik-Chervonenkis dimension arguments. So you look at the okay. So basically, in W, if you look at the columns, each of them has a support, and those supports turn out to have finite Vapnik-Chervonenkis dimension, and from this, then it's not hard to prove. And using the standard lemmas, Shalla lemma, if you know what it is, you can estimate this packing number. So this is one theorem, and let me conclude with a conjecture, which is one of my favorite conjectures in the area. And Balázs Szegedy, who is my quarter on all of these, and I have tried this really hard to prove, but I think it should be true. So for this, just a few minutes of some more definitions. Suppose that I prescribe the density of, well, let me just, in W. Well, there are lots of W's for which, I mean, for a typical A1, unless this is 0 or 1 or something, then there will be lots of these. Now, suppose I prescribe the densities of several of these. The question is, can it happen that they determine W? Well, there is a... these are now arbitrary graphs, although the example will be bipartite, but it's a coincidence. So there is a theorem of Chung, Graham, and Wilson, which translates in this language as follows. If the density of, maybe I just draw it, an edge in W is some P, and the density of the fourth cycle in W is P to the fourth, then this implies that W is identically P. Now this is cheating. Their theorem is more interesting because they define this notion of a quasi-random sequence. A quasi-random sequence in our language is just something which tends to the identically P function. But if you work it out, it says that it's a sequence of graphs which look more and more like a random graph from the point of view of, say, densities of subgraphs. So so that means that T, F, G, N, for every F tends to P to the number of edges of F. So this means quasi-random, and they give a number of very interesting equivalent conditions. It's a classical paper for this. The most surprising is that this condition is enough to require. It's enough to require this condition for these two graphs. So if the edge density and the fourth cycle density tends to what it should, then every other graph has the right density and all the other nice properties hold. And now if you go to the limit, then it just means this. It just translates into this. And so this is an example where two special densities determine the function. And we say that W is finitely forcible if there exists F1, Fm, A1, Am, so that W is the only solution. You have to be a bit careful here because you can always apply measure-preserving transformations to the variables, but let's discard those and disregard those. And so. So this is the notion of a finitely forcible graphon, and it turns out that there are quite a few of them, not only the constant function, which was the first example. So every one of these, which are step functions of this type. So what you get is here, those are finitely forcible, and whatever this function is also finitely forcible, and lots of others. And so the conjecture is that every finitely forcible one has finite dimension. And in fact, we don't know any which has dimension larger than 1, but it's unclear whether this is because they do have dimension smaller than 1, or it's just difficult to prove that they are finitely forcible once the dimension is higher than 1. These are not, it's not usually not easy to prove that something is finitely forcible. You can sort of come up with somewhat sophisticated sets of graphs and values. And now this final sentence, these finitely forcible graphons are sort of, if you look at an extremal problem in graph theory, you usually have a sequence of extremal graphs for every n. And quite often these are convergent, and they will tend to some graphon. In fact, you can prove that if they are unique, essentially unique, then they tend to some graphon, which is therefore something like a template for this solution. And this graphon tends to be finitely forcible. So somehow it would say that solutions of extremal graph problems are finite dimensional. They have polynomial size, regularity partitions, and so on. So it would have a number of interesting applications or consequences. Thanks. I'll stop here.
But you also know examples of finitely forcible that don't seem to come from any extremality properties?
No, I mean, it depends how you define extremality. Yeah. You can always say that they minimize the sum of squares of differences here. No, it's illegal. I mean, you can expand it, and so you can always write it as a linear combination of these of such densities. You want to minimize a linear combination of such densities. We conjecture that they all have finitely forcible solution that we cannot prove. But it seems to be the case.
Some natural extremal problems that fit into this.
Oh, for example, minimize the number of triangles given that, minimize the number of edges given that there is no triangle, two-round problem. And, or given the edge density, minimize the triangle density. That's a hard problem, which was just recently solved by Rasborov. So it's already this. It's given the edge density, what is the minimum of the triangle density is a difficult problem. So this includes a lot of such interesting questions.
Okay. Any other questions?
So you think this would kind of imply there is a unique, in some sense, a maximal, extremal graph?
So the idea is that if it's not unique, you can add a little perturbation and make it unique. So you say that we are maximizing this, and subject to this we also want to maximize this, or add it with a multiplier. There are all sorts of ideas, but we don't know how to prove that it's always doable.
Okay.